Hello everyone. So let's do the next set of 5 questions, question 17 to question 21 of the 2020 NET question paper, okay, June 2020. And as you know, I am doing only the organic questions. So the first question is question number 17, the major product formed in the following reaction. So we are having a alkyl chain. At one end we can see we have alcoholic group, other end we are having one halide group. And first we are adding NSNH2. NS, you can see here they are given 2-nitrobenzene sulfonyl amine. So though it is amine, but because it is beside sulfonyl group, it is an acid, it will act an acid, it will give proton. Apart from that, what you see here is dead is there. Dead is diethyl azo dicarboxylate. So if you see dead or diad, please remember it has to be a Mitsunobu reaction along with PPS3. So what does it do is basically Mitsunobu reactions for esterification kind of stuff where inversion of configuration happens. I'll explain sometime. Then second reagent in the second step which is used is cesium carbonate and tertiary tetrabutyl ammonium iodide. So yeah, so the cesium carbonate is basically a base, but very important point about cesium is cesium 2 plus, it always favors intramolecular reaction rather than intermolecular reaction, because it has positive charge, it will hold the electron charged species in the same species together through intramolecular interactions. Okay, and what is this tetrabutyl ammonium iodide? It is basically we add I minus. So if we want to add I minus in organic reactions, we cannot add Ki or some other inorganic salt because they will not dissolve. So when I want to add I minus, I need organic salt. So we use something like tetrabutyl ammonium iodide. So this I minus will basically help. I minus is a very powerful nucleophile, one of the best, most powerful nucleophile. So it helps in removing bromide kind of stuff. And once I minus is there, I minus is a definitely trillion times better leaving group than your Br minus. So we'll be using for that. We'll see later what happens. Then thiophenol and KOH is there. We'll see that step. Okay. So first step. So first step has to be Mitsunobu reaction. Yeah. So what happens basically, what Mitsunobu does is remember we add PPS3 on the oxygen. See, PPS3 phosphorus never happy with +3 oxygen state. So this will go on attack and it becomes phosphorus gets +4 oxidation state. Okay, and then what happens, phosphorus likes +5 oxidation state, then slowly this will get out, it will go out as POPS3, and then what happens is when it leaves, so another nucleophile, so generally CO minus is a not strong nucleophile, but it becomes such a good leaving group because POPS3 is a wonderful leaving group. So this will attack from behind and this inversion of configuration. Please see here what happens, you are getting a ester, but generally what we will think is this OH is there, it will go and attack with some acid halide or acid anhydride, but here we directly use acid, and then because it is leaving we get inversion of configuration. Similarly, it can be used for other reaction, something like you can see here, azide formation also occurs. So mechanism is not very important from competition point of view, because competition of point of view you have to just understand reversal of configuration happens. Why it happens? Why it happens is because O attacks PPS3 and leaves as POPS3. That's the driving force, and this gives inversion of configuration. And please remember, for Mitsunobu reaction we need acidic media. It has to give proton, so this one acts as the proton source. This proton is taken, and we will see the mechanism. Okay, so I'm going slowly, please keep reading, you can keep pausing it. Now first step is triphenylphosphine attacks dead, so diethyl azo dicarboxylate. So this is ester, this goes in here, and this negative charge is delocalized, and this negative charge will take away proton from the acidic medium source. And then what happens is, you see here, this is +4 oxidation state, and then this alcohol goes and attacks this phosphorus. This is what is important. Phosphorus has great affinity for oxygen. So first phosphorus attacked, now phosphorus is being attacked by oxygen, and then this proton, this arrow little bit I should have drawn like that. So this proton is taken away, it becomes OH, and then oxygen comes, attacks here, this leaves, and you get oxygen positive charge, and this leaves out like that, and then this same NH2, this goes and attacks here, and this POPH3 leaves, and so it's kind of amine formation has occurred, right? Now next step is cesium carbonate. Now cesium carbonate, as I was saying, it acts as a base. It's a very special reagent, and it is highly electropositive. So what it does is it gives away bond pair of electrons between cesium and oxygen towards oxygen, making carbonate anion quite strong base, right? So what happens when you go from top to bottom? So electropositivity increases because you understand size is increasing, and so the nucleus effect on outside is much lesser. So it is more electropositive as we go down. So like when you go from Li plus to sodium plus to K plus, electropositivity increases. Similarly, the CS2 plus is highly electropositive, and therefore carbonate is having complete all the negative charge. It's a charge interaction, therefore it's a much stronger base. And apart from that, what is very important is cesium coordinates at the two ends of molecule, and thus it favors the intermolecular attack. So, and again what happens, what does I minus do? When Br is there, no, it may not be very favorable for SN2 reaction if something else has to go and attack. Nucleophile is not very powerful. You want to, if nucleophile is very powerful, then Br minus is a good leaving group, SN2 reaction will be very favorable. But imagine if this nucleophile is weak, then what do? Is we add iodide first. Iodide is a very powerful nucleophile because iodide is less electronegative than bromide, therefore lobe is much bigger, so interaction of orbitals is much better and becomes this, and that I minus is a very powerful leaving group, much better than your Br minus, and therefore nucleophile can attack here and this I minus leaves. So what cesium carbonate does is, first thing is it removes proton from here. You can see here carbonate removes proton from here, you get negative charge. Now this negative charge and iodine's lone pair, they coordinate with this cesium, and then what happens is, because it is brought together, a new molecule, new N minus cannot attack here because cesium is holding this part together. So if you think that another molecule will come and attack, that will not happen if cesium ion is there. So it has to be 100% intramolecular attack, and this S minus N minus attacks, this leaves, and you're getting this species. Next is thiophenol. Now thiophenol is more acidic than your phenol. Apart from that, because sulfur will stabilize negative charge better, and now sulfur is a very powerful nucleophile, much powerful than oxygen, because lobe is much larger than oxygen, and therefore this will go and attack on the sulfur. Here it comes, and then this leaves, and you're getting this product. So answer is option D. The next question says, correct sequence of reactions involved in the following transformation. This was quite easy question actually, though it looks quite complicated, it is quite easy. So you are having cyclohexanone, you are using a powerful base which is sodium ethoxide. So you can see here it's a ketone on which alpha carbon there is a proton, so it has to be aldol reaction. If it was not there, it would have been Kenzaro reaction. So, and generally what happens is, it will never be aldol reaction, to be aldol condensation, because it leads to formation of thermodynamically stable alpha beta unsaturated ketone. Okay, so sodium ethoxide pulls away proton from here. I will show you the mechanism anyway. And what is difference between reaction and condensation is, reaction, just reaction occurs and you get a hydroxide. Condensation, at least one molecule has to be lost, and generally the molecule lost is alcohol. So first step is this proton is removed, you get negative charge, and now there are two things, like you get a negative charge on carbon, and another chemical structure you can see negative charge on oxygen. So basically you are having negative charge density on oxygen and carbon, but carbon of course is a much powerful nucleophile than oxygen, because nucleophile is interaction of orbitals. Oxygen is more electronegative, so it holds its electrons closer towards itself, small lobe. It is not able to interact very well. But carbon lobe is much larger. It's a very powerful nucleophile. So this will go and attack on this, and this leaves. So this is till here it is aldol reaction, but this OH minus will leave because sodium ethoxide will pull a proton from here, and this OH minus leaves, and you get a thermodynamically stable alpha beta unsaturated ketone. You may get a doubt, this OH minus is bad leaving group. How does it leave? So if you think that a nucleophile will attack here and then this OH minus leaves, that will not happen. OH minus is definitely a very bad leaving group accordingly. But if you give negative charge on a neighboring carbon, then this leaves, because then is overlap of orbital, and then this OH minus leaves and you get double bond. That is happily seen. It's more like not OH minus, is water is being lost. So first step is that. Now next step also looks quite clear, because you are having alpha beta unsaturated ketone and you are having of course starting material there, so cyclohexanone is there, so it has to be Michael addition. Michael addition is 1,4 addition reaction. So what happens, you I will go slowly, you can keep reading also. Yeah, so cyclohexanone is there, this proton is removed, you get a negative charge. Now this negative charge will go and attack alpha beta unsaturated ketone. It was same, I made it like this so that it starts looking shape in the same molecule, how in the same way how they have given in the question. So this goes and attacks here, it comes here, you get negative charge, this comes here and this comes. So this is your 1,4 addition. Next step is aldol reaction. It takes away proton, you get negative charge. Now this negative charge will go and attack here, you get OH. So this is your aldol. So the answer is, first is aldol condensation, second is Michael, and then third one is aldol reaction. So answer is option A. Question number 19. The major product formed in the following transformation. So when you see something like this, when you are having diene is there and in between C double bond O is there. It's a conjugated system. So whenever you look at it, no, please understand it will be Nazarov reaction. It's a pericyclic reaction. It's a electrocyclic reaction. So what happens is, for pericyclic reaction, for this electrocyclic reaction, we know that we need a conjugated system. So what happens is, FeCl3 we know is a Lewis acid. So first step is, you can read all this. Yeah, first what happens is, oxygen attacks this FeCl3 and this comes here, you get a vacant p orbital. Now the system becomes conjugated, because there is a p orbital here, there is a p orbital here, there is a vacant p orbital here, and there are two more p orbitals, all are overlapping. Now it becomes conjugated systems. Now it can go electrocyclic reaction. Now how many pi electrons are there? 1 2 3 4. So it is 4n system. 4n system. So for electrocyclic reaction, you have to remember just one formula, everything else can be done. It is 4n h nu dis. That's what I remember. You can remember something else also. So if 4n system is there and you do under photochemical condition, it will be dis. So when 4n electrocyclic reaction happens under thermal condition, here it is thermal condition, because they are not specifically telling light. So even if it occurs at 0 degrees Celsius, it is thermal. It is hot compared to -1 or -2 or -20, right? So all these are, so that should be con rotatory. If it is 4n plus 2 system, then h nu will be con, thermal will be dis. So now we know this rotation will occur, con rotation. Why it occurs, that also I'll explain in a jiff. So electrocyclic reaction occurs, this attacks here, this attacks here, you're getting this. Now it could, you can also say, because pericyclic reaction, it means that arrow you can draw from both sides. So you can say that why not like this and then like this. That also is possible. Only problem is, in that case you would have got double bond here and positive charge here. So reaction always goes according to kinetics. The intermediate should be stable. So if positive charge is at a carbon, beta to carbon silicon bond, then what happens? It is very stabilized. Why does it happen? It is basically silicon is more electropositive than your carbon is more electronegative. So you know something like Grignard reagent. So what happens in Grignard reagent? Carbon attached to metal is more electropositive. That means carbon is having electrons. So this sigma bond, even the sigma bond becomes nucleophilic, and we know it can go and attack your electrophiles. Similarly, RLI. So if carbon is attached to a more electropositive species like silicon, then the sigma bond becomes uh, electron donating, becomes nucleophilic. Also carbon silicon bond is quite long. See, carbon silicon size is very different, and therefore this can donate electron nucleophilic in the vacant p orbital uh, quite well, and therefore this carbocation is stabilized. And then what happens is, now keep reading also slowly, you can pause it and read it. And then Fe has got negative charge. So when Fe has got negative charge, all the bonds from Fe is nucleophilic. So this OFe bond is also nucleophilic. So this comes here, this picks up proton and you get this. Now what happens is, now workup is there, water is there, OH minus has come out because proton was taken from water. Silicon has great affinity for O minus or F minus. Why? Because silicon is more electropositive than carbon. So it's lot of positive polarity is there. So it's a charge interaction. It's not nucleophilic attack. It's charge. So lot of positive polarity is there. So negative, where concentrated negative charge is there, it will attack. So I minus will not attack because iodine is much large in size. So this negative charge is delocalized. What we need is hard base. What we need is charge interaction. So fluorine is very small in size, very electronegative. So it holds all its electron close to itself. Same way oxygen also. Therefore, they have strong affinity for silicon. So this goes and attacks. This comes here, and you get this. Okay. Now, yeah, and apart from that, this hydrogen has been attacked from away from the viewer. Why? Because the silicon was towards the viewer, and therefore this goes this water will attack from behind to avoid steric hindrance, and then H is behind. Now we also need to find out stereochemistry of these two carbons. That will be known in this step where you are having electrocyclic reaction. Only thing, we have to follow this Kohn rotation because we know that it is Kohn rotatory, and then see where the hydrogens are there. Right now I have put wavy line, that means we are not very sure hydrogen is toward the viewer or away from the viewer. So we will try to explain why it is Kohn rotation. So basically psi 1, psi 2, psi 3, psi 4, because 4 pi bonds are there. So sorry, 4 p orbitals are there. So it will form 4 pi molecular orbitals. So these 4 pi molecular orbitals are psi 1, psi 2, psi 3 and psi 4. So it's for us easy to remember that at the end psi 1 will be plus plus, then it will be psi plus minus, then plus plus, then plus minus. If you want to know, it's very easy. In psi 1 there will be no nodes. So there are 4 p orbitals which is forming first pi molecular orbital. No nodes means all signs will be same. So plus 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 and plus. For psi 2 there will be one node, so it will be sign will change. Okay, so it is plus plus and then it is minus minus, right? And then there will be two nodes. Here and here. So it is plus minus minus and plus. So like that it occurs. Now what we have to consider is when we are thinking about ground stage, that is under thermal condition. In thermal condition you have to consider the molecular orbital in ground state. So this is the orbital which has electrons and has highest energy. so that will interact. But if it was photochemical condition, then what happens? One of the electron would have shifted here, would have excited and come here. Now this orbital has electron, has highest energy, so LUMO would have interacted, but which becomes HOMO at that time, which becomes HOMO at that time, you can say. And but right now downstairs we have to see side 2. So what happens? You are having plus and minus. So if some species is your 5 carbon, so it is something like this. Okay, so you are having plus here, yeah. So what we are seeing, top is plus, here it is minus, here it is minus, here it is plus, right? Now bond will be formed only when plus meets plus or minus meet minus. So if this rotates like this, only 90 degrees you have to rotate, okay? Then what happens? This also will rotate like this 90 degrees, so that this plus and this plus meets. Or this will rotate 90 degrees here, so that this minus comes here, and this also rotates like this, so that minus comes here. So then also bond can form. So what is very important is both the orbitals have to move in same direction, either clockwise or counterclockwise or anti-clockwise. So when both of them rotate in same direction, it is called as conrotatory. So here if we look, let us look here. So this is the we saw it is plus and minus. So top is plus, here top is minus. So here what I have shown is both of them are moving anti-clockwise. So this is moving 90 degrees, so that plus comes off here, right? Similarly, this also is rotating 90 degrees like this. So both of them moved in counter rotation, anti-clockwise or counterclockwise, so that this plus comes here, and so that plus and plus meets and bond forms. Now what happens to oxygen? So please understand, this hydrogen is in the plane and this p orbital is coming out of the screen. I am not able to draw this because I don't have 3-dimensional screen, but please understand, this is coming out of the board. So you are rotating it anti-clockwise, counterclockwise. So not rotating it this side, rotating it this side. You understand? It is rotating, this whole thing is that side, is going inside the board. So what happens? This hydrogen is coming out. Whereas here what is happening? Counterclockwise. So here again your p orbital is coming outside the screen, inside the screen, right? And clockwise we would have been like that, anti-clockwise will be like that. So when you are pushing it like that, hydrogen is also being pushed inside. So hydrogen is going inside and this hydrogen is coming outside. I know it's a bit tough to understand, think about it. You can look into other YouTube videos also, but please don't move ahead if you don't understand what is called this rotation, how this hydrogen both came outside. And then last step, we have already told this, silicon is lost, and that's what it is. So answer is option D. Moving on to the next question. This was one of the very tough questions. Unless you have seen this molecule, this reaction is tough to immediately imagine all those reactions here. But let us understand the basic concepts of organic chemistry here. The major product formed in the following reaction sequences. So first molecule is this, and then you are having this. So when you see something like this, please understand it is a Wittig reaction. So Wittig reaction, what happens? In Wittig reaction you are having a aldehyde, right, or ketone, and then you are having another species where PPS3 is there, and double bond some species there, C, and then let us take H and R. Okay, H and R, let us put here also. So we know phosphorus is not happy in double bonded with carbon, it is very happy double bonded with oxygen. It's a huge driving force for Wittig reaction. P double bond O, PPS3, this leaves, and so this double bond continues here, like this POPH3 goes and this forms of alkene, this forms of alkene. That is what is Wittig reaction. That is what is Wittig reaction. Now Wittig reaction, what happens is, generally Wittig reaction gives you thermodynamically less stable alkene. Okay, that means the two bulky groups will be on the same side and less bulky groups will be in the same side, so sterically hindered. but that is normal Wittig reaction. But in this, if you see this Wittig reaction, we are using phosphorus ylide. This is stabilized phosphorus ylide. So what happens here is basically you are having PPS3. So carbon phosphorus bond is very long, okay, because size difference is there. So the pi bond is not very effective. It's pretty much like phosphorus has positive charge and this carbon has negative charge. You can show one of the chemical structure double bond, but this is more right structure than this one, okay. Now you are having CH and you are also having COOET. So what happens here? This negative charge is actually delocalized. This negative charge is actually delocalized. It is delocalized between this carbon oxygen. So because of that, this is stable. So it is not in a hurry to attack. So generally it is in hurry to attack. It goes through a more stable intermediate, but it ends up giving less stable product. But when it is stabilized phosphorus ylide like this, it goes through unstable intermediate to give you a more stable product. So I'll explain you as I go down. So whatever side is written here, please keep reading it. Yeah, this is stabilized phosphorus ylide. So now I'll explain you how it happens. So basically CHO is there and this whole thing I have taken as R, and this here again this I have taken as R. So imagine if this was not stabilized, then what happens? Mechanism is always like this. They two attack from opposite directions. So imagine if this your aldehyde is there, so this will attack like this. Initially the interaction between this and this occurs, so they come close to each other, so that the bulky R group will be as far as possible from the other R, and you are having your double bond PPS3, right? PPS3, if it was not stabilized, I am saying. So now this is a much stable intermediate because the two bulky groups are there and these two interact. So you are having this negative charge here and positive charge here. So let me delete of this bond, so that this goes and attacks on this, and then rotation occurs. So when the rotation occurs, the two R group comes on the same side and you get thermodynamically less stable product. But here, because the phosphorus ylide is stabilized, it can wait. It is in no hurry to go and immediately attack. So it goes and attacks in a way that it goes through unstable intermediate but stable product. So see this is unstable intermediate. These both bulky groups are on the same side and both less bulky groups are on the same side. So this goes and attacks here, this comes here. This is what is called the betaine. So betaine is not ring. I have seen one mark question sometimes they ask. So betaine is not the ring, and then rotation occurs. You can read all this. Yeah, basically now it rotates 180 degrees. So when it rotates, both are in opposite directions, you get a more stable product, and this is called as oxetane ring. Please remember, this is also important, okay? This is called as oxetane ring. And then POPS3, I said POPS3 is very good living group, like very stable species, that is the driving force. So this comes here and you get this thermodynamically stable E alkene. E means the bulky groups are in opposite direction away from each other. So here also pretty much same thing will happen. So this POPS3 will be lost and you get a thermodynamically stable alkene. This COOET, the bulky one, and this bulky group, they are opposite to each other. Similarly, these two hydrogen are opposite to each other, right? Now moving on to step 2. So step 2 is you are heating it again. So now generally when you see a heat, no, it has to be some pericyclic reaction. So it can be sigmatropic rearrangement, or it can be Diels-Alder reaction, or it can be your what did we talk just now? it can be in reaction, another one electrocyclic reaction. But here if you see carbon oxygen bond, generally it will break. Why it breaks is because it will lead to formation of carbon oxygen double bond. Now carbon single bond, sigma bond, in this is very interesting. Carbon carbon, if you see carbon carbon sigma bond is much more stronger than your carbon carbon pi bond. But in carbon oxygen it is different. The pi bond is more strong than your sigma bond. So I know the values of it. I think carbon oxygen single bond bond energy is 69 kilocalories per mole. Okay, but pi bond is 69 plus I think it is 85 extra. So the pi bond releases more energy because it's not just orbital interaction, it also becomes charge-charge interaction. So more energy is released when pi bond is formed, and therefore pi bond formation in carbon oxygen is a very strong driving force. So it will undergo what is called as 3,3 sigmatropic rearrangement. So I drew it like that, but I should have drawn something like I'll show you here, so it's better. Yeah. So what happens is here it breaks. So counting, how we do is we see where the bond breaks and we count both sides. So since bond is breaking here, so I'll count here 1, 2 and 3, and here also 1, 2 and 3. And when the bond forms, you look at what is the number where bond is formed. So bond is forming here, so here it was 3, here it was 3, and therefore it is called as 3,3 sigmatropic shift. And count that 3 plus 3 is 6. 6 means it is 4n plus 2 aromatic system, so it will undergo under thermal react conditions. If it was not, it was something like 1, 1, 3, then 3 plus 1 is 4, then that would have been under photochemical condition, right? So here what happens is this breaks here, this comes and attacks here, it comes here, and you get this product. Now you get C double bond O, huge driving force, and that's why it undergoes this rearrangement. This is called as oxycope rearrangement, where carbon oxygen bond is being broken. Next what happens is, see, this is anyway not stable very much because aromaticity is lost. So again it will undergoes another rearrangement, what is called as cope rearrangement. So that's why I was telling you it was not very simple question, because it's tough to imagine two reactions in the same step with just heat. So this undergoes, again here it cleaves, so this bond is broken. So 1, 2, 3, 1, 2, 3. You know it is 6 electrons involved because 2 pi bond, 2 plus 2, 4, and 1 sigma bond. So it is 6 electrons. So aromatic transition state, therefore it occurs under just thermal condition. So this opens up here, this attacks here, this attacks here, and you are getting this species. Now this is not stable because aromaticity has to be gained back. You had lost the aromaticity. So this comes and attacks here, you get this, and now still this OET is here in open chain, so it will undergo what is called as transesterification. So this OH will go and attack here, this comes up, goes down, and this OET leaves, and you get this product. So thus the answer is option number D. Last question for this video. So you are having this molecule and you are reacting it with formaldehyde, HCHO, and camphor sulfonic acid. Now camphor sulfonic acid is very powerful organic acid. It is like sulfuric acid, only thing it is organic. So when you see something like this, please understand you are having a aldehyde. Aldehyde or ketone, they are generally not good electrophile, like there is not enough positive polarity for nucleophile to attack here. So if you want it to become nucleophilic, you have to get positive charge on this oxygen. So generally it will attack of proton, like here it has attacked with camphor sulfonic acid, or attack Lewis acid, something like FeCl3 stuffs like that, or AlCl3. So here it attacks, I must have drawn that, yeah, it's camphor sulfonic acid, so it goes and attacks this proton, you get a positive charge. Now it becomes very good electrophile. Now here you have to look what all can attack this carbon carbon double bond. So pi bond is there. Pi bond, see, for anything to attack as a nucleophile, what you need is you need high energy. Electrons should be maximum energy. So lone pair has higher energy than your pi electrons, okay, then you have pi, then sigma. So clearly this pi bond will not attack, either oxygen can attack or nitrogen can attack. Now in that also which has higher energy, oxygen is more electronegative, that means it likes electron, so electrons are more happy, so it is having lower energy, whereas nitrogen is not is less electronegative, so electrons are not very happy, so it is having higher energy. You can also think as oxygen is more electronegative, so it holds electron closer towards itself, the lobe is smaller, whereas nitrogen, what happens, lobe is much larger, because less electronegative, so it's a much more powerful nucleophile. So this will go and attack here, you get this species, and then this takes away proton, and then nitrogen goes and attacks here, this water leaves. So till now it was simple. After that what happens, this will undergo 3,3 sigma tropic rearrangement again. Why? See, basically this sigma bond breaks. It's not easy to break sigma bond, but why does it break? So if you think about SN2 reaction, you are having carbon, you are having a leaving group. How does leaving group leaves? It leaves because, it leaves because on its anti-bonding molecular orbital, nucleophile goes and pumps electron, yes? So when the nucleophile pumps electrons in the anti-bonding, then bonding molecular orbital becomes weak and it leaves. Same way what happens here is, this carbon-carbon bond is there, carbon-carbon bond is there, so that means it also has a anti-bonding. I should have made little bigger and this one little smaller. Anti-bonding molecular orbital is there, so this oxygen pumps electrons in the anti-bonding, making it weaker, and therefore now you can count, because it is breaking here, so it is 1, 2 and 3. I should write here 1, 2 and 3, and here also it is 1, 2 and 3. So this goes and attacks here, this comes here, you get like that, and then this oxygen comes and attacks here, so this will go and attack here like that, and this comes here, and you get this product, and this proton is taken away, you get this. Answer is option B. Okay, that's it for today's video. Thank you very much.